Hello, and thank you for tuning into episode 6 of the Exebenus podcast series Life Pulse. I am your host, Anna-Siv Uberg, Vice President Marketing and Commercialization for Exebenus. Our Life Pulse series is all about the transformative power of digitalization, machine learning, and automation in oilfield operations. In the last episode, we talked about machine learning in general. In today's episode, we will continue focusing on machine learning and how the technology can be used to predict situations that may cause a stuck pipe. For this, I will be joined by Exebenus product and research data scientist, Tim Robinson. Thank you for joining me, Tim.
Glad to be here.
Stuck pipe is a common risk in almost all well operations, from exploration to production. Not only does stuck pipe create hazardous situation, it also results in costly, non-productive time, and can, in extreme cases, ruin the well completely, which means the operator has to abandon the well and start over. For these reasons, stuck pipe is a risk that must be managed. Tim, how can machine learning help?
Before answering your main question, let's quickly go over what ML is for our audience in case they missed our previous podcast before addressing stuck pipe. So machine learning refers to a set of computational and mathematical tools that let us build statistical or predictive models without having to explicitly specify all the model parameters. These are inferred from example data or training data, as sometimes it's called. So common applications include regression, that's predicting some continuous number, classification, predicting some type of categorical label or labels, and another could be anomaly detection. So a classic regression example would be building a tool to forecast sales to assist in inventory management. Fraud detection could be a great anomaly detection example. We discussed some of these on the previous episode, so if anyone would like to go back and check that out. So how can machine learning help with stuck pipe specifically? So I'll talk about our case in this episode. So what we do to help stuck pipe, we develop models and systems which contribute usefully towards the goal of predicting risks of stuck pipe. So regression, classification, and anomaly detection approaches could all be used for this, depending on how we formulate the problem to be solved, and also what information is practically available.
So just to clarify, you're saying our machine learning agents are used to predict stuck pipe.
So there's a subtle difference here. We use machine learning within a system that attempts to identify risk of stuck pipe and provide early warnings. Whether a stuck pipe actually happens or not depends on a complex mix of factors. So we have focused our machine learning tools on three of the most common causes of stuck pipe. These are differential sticking, mechanical sticking, and hole cleaning. Differential sticking is mainly related to static friction due to pressure differences between the formation and well fluids. Mechanical sticking is related to dynamic friction as the drill string moves through the wellbore. And hole cleaning relates to pack-offs, poor cutting to transport, and generally is a higher risk in very fractured formations.
What does that look like from a higher level perspective?
The Exebenus ML agents work by predicting how certain key variables are expected to evolve in the near future. And then they flag risks based on analyzing these predictions with respect to known risk factors which are defined by drilling engineers. So then anomaly detection is performed based on looking for kind of odd behaviors in these predictions conditioned on recently acquired data. So it's worth noting that there are some other approaches that could have been taken, for example, more conventional simulations or physical models and comparing observed data to the outputs of these. But we chose to develop our own approach based on machine learning and statistical modeling.
What does that mean? How does the Exebenus approach differ from the conventional standard approach?
Let's just expand our definition of general or conventional approaches here. Aside from physical simulations. So you could also have human monitoring in operation centers directly. There could be interpretation by the drillers on the rig side. Generally, these can be grouped together as real-time reactive warnings. So physical simulations are actually very powerful tools, but they can be quite difficult to configure. Often many variables need to be set ahead of time, many parameters, and there can be some ambiguity in how to set these things, which is a potential source of error. So in Exebenus, we try to combine domain expertise for clearly defining problems to be solved with statistical modeling and data analytics techniques, which typically have more straightforward configuration requirements for the end users. So for example, for differential sticking, our system will identify breakover hook loads in real-time data and forecast these a few stands ahead using a regression model developed to do this, using data from many different wells around the world.
And why did Exebenus choose this route?
I think it's worth contextualizing a bit here. So machine learning is growing in usage and popularity within the oil and gas industry. In our case, we want to provide the earliest warnings possible. So having a forward-looking view on how some key parameter may evolve can help with this, potentially identifying the risks earlier than systems which are more reactive in nature and trigger off current observations. The simpler configuration and setup requirements for statistical model-based tools, which I mentioned earlier, is also a key factor here in choosing to take this route. So going back again to the differential sticking example, the goal is to encode the past experience about differential sticking from many wells into the machine learning model itself, rather than just using information from the current well and reacting to it. If we have a view of how the breakover hook loads will evolve in the near future, then early warnings can potentially be raised based on this.
I like the idea of predictive. It's like the weather forecast, very helpful when you're planning outdoor activities. For the more machine learning savvy, what is another analogy to help us understand the Exebenus approach better?
Sure, I can expand a bit on what I mentioned earlier. So continuing again with our differential sticking example, this forecasts and monitors the breakover hook loads, which are the points at which static friction are overcome in a time series of the hook load. So using sequences of the recent breakover hook loads and the knowledge of past observations of hook load sequences, which we capture in the model's parameters, we can estimate near future behavior of the breakover hook loads. So if we see some unexpected forecasted increases in static friction, or generally anomalous behavior in an output sequence, this can indicate the risk of differential sticking or some other dysfunction potentially about to happen.
Let's get back to the practical concerns our clients have about machine learning. We know they worry about data. It sounds like you need a large amount of specific data before you can consider using machine learning. Is that a correct assumption?
So we should draw some distinction here between building ML tools and using those which are already built. The data requirements for these can be a bit different. So for the former, there's no strict answer on how much data is needed. This really depends on the specifics of the problem that is being solved. For the latter case of users, specific quantities of interest need to be measurable and usable in live operations. So the availability of data is key rather than the sheer quantity, so regular availability. In terms of practical concerns, from our experience, typically prospective users would like new tools to be, quote, plug and play with real-time systems that users already have. So we want smooth integration, effectively, at its core. So these sorts of tools might include a viewer like Sitecom Discovery or some existing data infrastructure. So often clients actually have all the data they need in order to use these sorts of tools. And we try to build our products using data that engineers and rig crews are already familiar with. So to expand on this, we primarily use surface measured data that has very high availability. So we try to reduce the dependence on downhole sensors and vendor-specific tools wherever possible.
Can you give an example of the sort of sensor data that you use?
Sure. So in our case, like I mentioned, the surface data is generally what we are most focused on. So we use the real-time data available from the electronic data recorders. And some of the variables of interest that we would look at would be the real-time hook load readings, the standpipe pressure, mud flow rates, the mud density going into the well, if that's available, and other things such as the bit depth and hole depth and ROP.
So mostly readily available surface data. That is great news. Okay, so what about the data quality? That's another question we get a lot. Our clients may have a lot of data, but the quality is not always appropriate. At least that is what they assume. Can you comment on the data quality considerations?
Data quality really spans a spectrum rather than being easily categorized into a binary good-bad label. It's typically possible to gain some value with non-ideal data. So even if machine learning models perform less well on a noisy data set or something with some other known imperfections, it doesn't necessarily mean that every single metric that you use to assess these models is just going to go to zero immediately because of some known issues in the data set. So as a result, I think it's very useful to have an idea of the uncertainties or error rates associated with any given machine learning model that's in usage. This should be helpful for informing decision-making processes that relate to the usage of these machine learning models and the kinds of confidence that you should have in their outputs in a given scenario.
Earlier, you mentioned training data. Can you explain the concept further?
Yep, training data. So I think it's worth first defining what training refers to. This is the process of fitting the parameters of a statistical model. Sometimes this is also called learning in the field. So the data sets we use to do this are the training data sets. So these might be offset well data or just historical data more generally. For supervised learning, which probably is the most commonly used in the industry, training data will have both independent variables, which are sometimes called inputs or features, and dependent variables, which are often called outputs, targets, or labels for classification models. A supervised machine learning algorithm will attempt to find the model parameters that result in some optimal mapping of the training data's independent variables, the inputs, onto the dependent variables, the outputs. For example, linear regression assumes a linear relationship between independent and dependent variables. Strictly speaking, it's a model that's linear in its parameters, and it identifies the model parameter values that minimize the sum of squared errors between the dependent variables from the training data and then the values predicted by the model.
Thanks, that really helps. Okay, here's another question for you. We get this a lot as our clients are transforming their operations and trying to increase performance across all of their assets. How is it that machine learning models built for one region can be applicable in another region?
We call this model generalization. And thus the key question is, how do you define a modeling process that supports out-of-the-box usage in different geographic regions, with different well types, etc.? Many operators will have global drilling operations, so the ability to use the same tool in many different places is really desirable. So how practically can we achieve this out-of-the-box usage? Firstly, it's good to consider the dataset construction. This means that you have examples of different types of wells present within the various subsets of your data, so you have a representative sample. Once information is made available to a model, we still need to exploit it usefully. So a machine learning model must have enough complexity to model the various underlying data generating processes without being so complex that it effectively memorizes the training data set. This is called overfitting, and performs very badly on new data.
How can you prevent overfitting from happening?
A good approach is to bake generalizability into the model building process itself. We want maximal independence between training, validation, and holdout testing subsets of the data. For example, if we use a neural network with what's called early stopping, and the validation set is made up of independent wells from the training set, the model will stop training once the generalization to the validation set after each training iteration appears to worsen. So for holdout testing data sets, we can get an estimate of how well a model will perform in the wild. You may have heard this referred to as out-of-sample testing. And finally, another important consideration is to properly communicate the limitations of these models to users based on the validation exercises described above. We want tools to be used within their realms of applicability. It's a responsibility as product providers to let users know where and when not to use the tools. All models will be overfit to a certain extent, so that's why it's really key to get these limitations out in the open.
Are there other limitations of machine learning for applications such as stuck pipe?
Sure. So there are some other limitations to consider aside from the model generalizability that we described before. So we actually discussed some of this in the presentation we gave at the IADC 2021 conference, which is available on Exebenus's YouTube channel. Shameless plug, I know. So if you have sudden events which inherently lack early warning signs, these are of course not predictable. If you have a wellbore instability or a sudden collapse or breakage of a formation, then no matter what tool you have, you're probably not going to be able to predict this. So that's obviously a fundamental limitation. Another example of where you might see this kind of behavior is in the price action of stocks in the equities market. So the events that tend to cause very large movements in prices are often surprises and are just not predictable from the historical values of the stock price. So another thing to consider is previously unseen behaviors or phenomena, which are just, by that I mean it's things which are not in your training data sets, are unlikely to be modeled well directly. So all is not necessarily lost here, because in our formulation, these kinds of unseen behaviors may just lead to very abnormal outputs from the model. And this is another way that we can trigger warnings, even if the predictions themselves do not turn out to actually be close to the observed values when they come in. So data quality does remain very important. However, what people perceive as sufficient data quality may not always match reality in either direction of wrongness. This spectrum of quality is key to consider. But then, as you might imagine, as the quality of data gets worse, that imposes more limitations on how you can use your models based on a reduced confidence that you would associate with their outputs.
In today's economic environment, timely and better decision-making information is important for increased productivity and reducing time and cost. Digitalization and automation are important, supporting initiatives.
Yep, agreed.
How do you see machine learning's role in this picture?
Machine learning means the real-time operations centers could be able to monitor and support more rigs and remote teams without needing to expand their human workforce. By supporting the monitoring specialists in their decision-making, this can help free up their time to apply their expertise more broadly. They spend less time on the simpler cases and can create more benefit by just focusing on the tasks which require the human intelligence touch.
So going back to your point about the operations center's ability to provide a heads up, do you have an example of how early a warning can be provided? Are we talking hours or minutes?
Sure, I can share an example from some historical data testing that we did, where we had a pack-off case which resulted in more than 20 hours of downtime, which included working the drill string and jarring. So the reason we use a historical test for this is that we have a clear reference of when an issue event actually happens, and the warnings which are raised by the tool can therefore be properly verified. It also means that the warnings which are raised do not interfere in any way with the operation. So we have a kind of a clear view of which warnings are false and which ones are true, or if any events were actually missed. So going back to the pack-off case, the hole cleaning agent raised a set of warnings 30 minutes and 20 minutes ahead of the issue, the pack-off issue recorded in the dataset. Now, we can't say for sure that this would have been preventable on this timescale, but having this early heads up can only be beneficial at this point.
Where do you see this going in the medium to long term?
Yeah, so in the medium term, I think we'll see machine learning in the form of objective decision support tools applied to all rigs operating in situations with stuck pipe risks or similar. Tasks requiring extensive domain expertise, I think, will be supported by software, but I think it's unlikely that humans will be fully replaced if there are any kind of major risks associated with these decision-making processes. So in the longer term, I think, and this is purely speculation at this point, I can't see the future, we'll move towards increasingly automated rigs as various technologies mature. And tasks which require less expertise will be gradually taken over by machines and other automated tools. So a smaller human workforce would be capable of fully managing a rig in these scenarios.
That is a very positive place to end this podcast. The potential for machine learning in this new working environment is definitely very exciting. There are so many possibilities, and we seem just to have scratched the surface. Thank you, Tim.
My pleasure. Thanks for inviting me on.
And thank you to our listeners. I hope this podcast gave you some ideas for how you can use and deploy machine learning in your operations. Watch for the next episode of LifePulse on the Exebenus website, on Spotify, iTunes, or wherever you listen to podcasts. You can also find the recording on our YouTube channel. By subscribing, you get an email when the next episode is available. Be sure to use the link on the Exebenus website or YouTube channel to send us your questions or comments. Thank you for joining us, and bye for now.